Hi, I'm Casey. I manage the traffic, chaos, and intuition teams at a company called Netflix. There's a few of us here. In fact, we have a booth straight back there. For those of you who aren't familiar, Netflix is a subscription service. How to explain this? So it's kind of like a library. You get a library card and you can go into a library and check out pretty much whatever book you want, and you can read books out of order, and you don't have to wait for commercials and things like that. So Netflix is like that, except we hire people to act out the books for you. So really the value proposition for Netflix is we save you from the burden of reading. And it turns out, like libraries, Netflix is really, really popular. So popular that we constitute about a third of the bits on the internet. And by far, most of that traffic is video traffic being served from our own private network. We run the world's largest CDN by far. And I think Dayton was here. I think so. Some of the people from the CDN team are here, and they can tell you that that's all really boring, right? Distributed cache expiry, solve problems. So instead, we're going to talk about the interesting stuff, the control plane. And the control plane is a microservice architecture that runs in 3 AWS regions: US West, US East, and EU. And I know there are a lot of companies here that have microservices. So in the first part, I'm going to talk a little bit about what a microservice means from a Netflix point of view. So I've got this realistic to scale drawing of our microservice architecture. All 7 of our microservices, I just gave them letters to anonymize the names because those aren't important. But and at top, you have a Netflix capable device. So we support thousands of devices going back to like Blu-ray players built in 2007 and stuff. And so a request comes in from a device, and it might hit a microservice. Service D in this case might be our reverse proxy, for example. And a reverse proxy isn't going to have all of the information it needs to satisfy a request. So it'll reach out to other microservices. In this case, service C might be, just to make up examples, might be a microservice that has information about movies. And service F might keep information about our customers. And they also don't have enough information to fully satisfy the request, so C reaches out to A, and F reaches out to B and G, and then A reaches out to B as well, and G also reaches out to B, which reaches out to E. And so you can see the requests fan out. And as the responses come back from the downstream microservices, the total response collates, and eventually service D returns a response to Netflix. So one of the interesting things to note here is all of those, the color doesn't matter, but those lines between them, those green lines there, can get a little bit messy. And in fact, I lied. We have more than 7 microservices. Here's a visualization of just some of the microservices in the streaming path. So there's request traffic. This is an animated GIF. So there's request traffic coming in on the left, and the different services fanning, the streaming requests fanning out to different microservices. And this is a small fraction. We actually have hundreds of microservices. And the interesting thing to note is that the interaction between all of these microservices gets kind of complicated. In fact, there's so many moving parts here that a human can't hold all of these pieces in their head. So we actually, by choosing this kind of design, lose some confidence in how our system works, because we don't have a chief architect at Netflix. We don't have an architectural board or a program manager per se who knows how each of these pieces fit together. In fact, it's easier to think of Netflix as having somewhere around 100 small engineering teams, about 5 to 7 people per team, who will own like a specific microservice. And they'll be domain experts in that, and they'll iterate on that on their own schedule. their own timeline without coordination. In a previous life, as a consultant, when I would see engineers take up a new project, I would often see that they optimized for one of these three things. The application's performance, its availability, that's its ability to respond in a degraded state, or its fault tolerance, its ability to recover to a correct state. And a more experienced engineering team would be able to optimize for some combination of all three of these variables at once, whereas less experienced teams tend to optimize for just one of them at the expense of the other two. And I'll posit that Netflix adds a fourth variable here, which is feature velocity. Now, from a process standpoint, I'm sure you've heard a lot about how to improve feature velocity, agile, lean, all of that stuff. But what I'm talking about here are architectural engineering decisions that optimize for all four of these things, including feature velocity. And so choosing a microservice architecture was one of those engineering decisions that we could make that helps us optimize for feature velocity. And there are other examples of engineering decisions that we make to make sure that our feature velocity increases, in particular, innovative and enabling technologies. So by choosing this microservice architecture, things get a little more, dare I say, chaotic. And we lose some confidence in not having a person that we can go to who knows how all of the pieces fit together. So in the second part of this talk, I want to take a little diversion into systems thinking. And I'm going to do that with a game called the beer game. Does anybody here have any beer on them? Nobody's pre-gaming? That's probably a good sign. Okay, so we'll just use our imaginations then. In the beer game, there are three players. There are customers who like to drink beer, retailers who sell it, and brewers who make beer. And I'm just going to take you through a hypothetical, kind of condensed version of this game. Now, so systems thinking is taught in like MBA programs, and they'll actually play this game. And usually the way that it's played is the class will be divided into these three teams. And the three teams will be physically separated, and they can only communicate to each other by passing back slips of paper, back and forth slips of paper that indicate desired intent to buy, a product exchanged, or money exchanged. And the point of the game is for the three teams to optimize for customer satisfaction, retailer and brewer profit. Simple enough. So starting off, I'm going to put some numbers up here. You don't have to follow the numbers. I'm just going to read through them for people who like to see them. So here we have a steady state description of, let's say, week 0, where the customer demand for this particular brand of beer is 1 case, and this is San Francisco, so let's call the beer startup beer, but we'll leave off the last vowel, so it'll be like startup beer, to be a little bit cooler. So startup beer is the product here. So the customer, so usually there's demand for 1 case of startup beer. The retailer keeps 2 cases in stock, so after the sale they have 1 remaining. So they order 1 every week, and the brewer has 8 ready for sale, and they're bottling 1 a week. So we've got a system in equilibrium, right? Steady state system. And here's where we want to start to tell a story. So here's the hero of our story. St. Patrick's Day is coming up, so I was gonna name the mouse like Mickey, but this is being recorded, so I can't say Mickey Mouse. So instead, we'll call him Carl. Carl the mouse is a very senior engineer, and he knows he has a lot of good ideas. He's made a lot of observations about the tech industry, and he's also a musician, as you can tell, because he has a guitar. And so he's thinking, if I can just work out this idea, like, fame and fortune will be mine. I just need, to connect with my muse and get this idea out. So maybe because he's a musician, he thinks he can find a muse in alcohol. So that week, he goes to the store with intent of buying 3 cases of some interesting beer. He sees startup beer and he goes, startup, that's perfect for me. That's what I want. Unfortunately, he can only buy 2 cases because the retailer only had 2, and so I put a -2 to illustrate the demand that was left unmet. The retailer wants to match the incoming demand, so they order 4 from their brewer, who has 8, so the brewer starts bottling 5. And that weekend, Carl shakes off his hangover and he writes out a manifesto, and it's brilliant. We'll call it the OpDev's Manifesto, and it's really brilliant. Basically, the essence of OpDevs is that you take operational optimizations and you apply it to developers. So, like, you take developers and you train them to type really fast to get their throughput up, and you make sure that they're hot swappable, right? So this helps us progress towards an immutable engineering team. We want boring, hot swappable engineers, because if they get creative, well, then they'll go talk about it and somebody might hire them away, and then you're left with this creative solution, and you bring somebody else in and they can't understand it because it's a creative solution. So really you want boring, dumb technology, never innovate, so that you can hot swap developers and just really focus on their throughput. So he posts this to Reddit and Hacker News and I don't know, Slashdot, and the internet takes off, and it's like, wow, this is great. And in the TLDR, he mentions, my muse for this, my inspiration was the startup beer. So the next week, customer demand for startup beer spikes to 64 cases. They can only purchase 5 because the retailer only had 5, leaving a remaining net loss there of 59. The retailer orders 65 to match the demand. The brewer sees this and has to build a second distillery to bottle more. And then we have an antagonist in the story, and I'll call him Dave. I actually modeled him after a real person. I hope he doesn't mind me mentioning. So David Hussman, who I admire for his originality and clarity of thinking. I won't mention his upcoming book, Product Agility, because it's not out yet, so I can't tell you how good it is because I haven't read it. No pressure, David. And he reads this OpDev's manifesto, and he tweets out just a scathing rebuttal. Absolutely scathing. I'll read the rebuttal in its entirety. Dude, no. And again, like, Twitter gets, there's so many faves and retweets of this that it brings down Twitter. And the internet's on fire. Like this rebuttal totally crushes this particular dream of Carl. His personal stock plummets. Carl coin reaches an all-time low. Yeah, Carl coin. If you have investor money, DM me. Yeah. Cloud on the blockchain. Think about it. So Carl's crushed. His dream turns out to be a bad idea. And so the next week, the only one who wants to buy beer is Carl to drown his sorrows. So the demand goes down to 3. And he buys 3, and the retailer then has 11 from the previous order. And the brewer now has 250 cases coming in. And the following week, we return to the steady state. So overall, the result that we get is that the retailer's left with 62 cases that they're probably not going to sell. They missed out on the opportunity to sell 61 to the customers. The brewer's left with 196 cases that they're not going to be able to sell at an extra distillery. WTF are they going to do with that? This is a terrible result, given that we were supposed to optimize for customer satisfaction and profit. So I'm not going to leave you with a terrible result up there. So let's look at the mouse instead and feel good about ourselves. But this game generally ends up this way, with this very bad result. And the point of the game isn't to make people feel bad. I don't think. I don't know. I'm not an MBA professor. But rather to point out that these 3 teams are comprised of smart people. And even though they're smart people, the systemic effect was highly undesirable. So in this particular case, this systemic effect is called the Whiplash Effect, where a small fluctuation in input leads to a drastic fluctuation in output. But more generally, we can say that this operates kind of like a microservice, where despite the skill, I mean, we'll leave intentions aside, but despite the skill of the engineers who own these microservices, these microservices might be provably correct, provably to spec, fully unit tested, functional integration tests, and yet the systemic behavior of them all working together can lead to undesirable results. So, so far, we're drowning and I've just been describing the water. So what do we do about it? So that's where chaos engineering comes in. Both of these examples, Chaos Monkey and Chaos Kong, have been mentioned in previous presentations here at this conference, so I'm not going to dwell too much on what they do, but I do want to reiterate their value and how they came about. So Chaos Monkey roughly kills instances in production, turns off instances in production during business hours pseudo-randomly. So Netflix had an interesting problem when they moved to the cloud, in that, just by nature of being on the cloud, they were guaranteed that instances were going to disappear. And if a critical instance disappeared and brought the service down, well, then that was bad news, and we all know that that always happens at 2 a.m. in the morning, and that's when people are groggy and don't make the best decisions, so that's unfortunate. And because of Netflix's engineering structure and culture, we don't have like a VP of engineering or a chief architect who could just proclaim everyone shall use these best practices for redundancy and fault tolerance. That mechanism just doesn't exist at Netflix. So instead, the genius of Chaos Monkey is it took the pain of the problem and brought it to the forefront for the engineers. So we call this being highly aligned to solve a problem, but very loosely coupled. Because of course we know what the best practices are to have a fault-tolerant or resilient system. Redundancy and fallbacks and all of that great stuff. So there might be a dozen different ways that each microservice can build itself to be resilient. And certainly experts were available if microservice owners needed assistance with that. But we didn't have to prescribe how to do it. We just brought the pain of the problem and put it in front of the engineers, and they solved it on their own, which was really powerful. And in fact, in like roughly 4.5 years of running this, we haven't had an outage due to a single instance disappearing. A testament to the engineers and the high alignment and the culture at Netflix that embraces this. So we thought, that's cool, that's effective. It works very well at the small scale, so let's apply it to the large scale. We have instances disappearing. Sometimes we have regions that go down. For whatever reason, Amazon won't give us an API to actually turn off a region. Thinking about other customers there. So we simulate it, but we simulate it often enough that it serves the same function, where it aligns the engineers to create their services to be resilient to a particular region going down, which occasionally comes in handy, like February 28th. So when a region does go down, the traffic team can move all of our customers out of that region to the other two, the service stays up. And we only know that works because we've run the Chaos Kong experiment often enough to make sure that it does. So we had these two working examples of chaos engineering, and we thought, okay, there's something here. How do we take this to the next level? And if I went around the industry to people who knew what these two terms referred to, or even internally to the company, and said, what is chaos engineering? Usually what I heard is, oh, that's when you break stuff in production, which sounds really good if you want to put it on your LinkedIn profile for a startup, maybe. but I can think, and I'm sure you can think, of many examples where breaking stuff in production provides zero benefit to the company. So we thought, okay, there's got to be something more to this than breaking things in production. How do we know when we're doing chaos engineering? How do we know when we're doing it well? And how do we know what to do next? And so we kind of locked ourselves in a room and came up with a formalization of this called Principles of Chaos, as we published it at principlesofchaos.org. And at a high level, we defined chaos engineering as a new discipline in software engineering that is the discipline of experimenting on a distributed system in order to build confidence in that system's capability to withstand turbulent conditions in production. So as we all know, stuff happens in production, and this is just a formal way of saying we can experiment to know how the system is going to react when stuff happens. So note that this is chaos engineering is surfacing the chaos that's inherent in a distributed system. It is not about making the system more chaotic or injecting chaos into the system. This chaos is already there, right? The fact that we have SREs tells us that the chaos is already there. Chaos engineering is a different way of bringing the chaotic interactions to light. Now I want to contrast this with testing. So in classical testing, you can kind of think of it like a function depending on what the scope of your code is. But so your code does something, and under certain conditions, you expect some output. And for a distributed system, you can view that as just composition of these functions. So notice that in testing, you're making an assertion on what the output is. And that's very useful and very good and necessary. But it's not really adding, strictly speaking, it's not adding new knowledge. It's just determining the value of existing knowledge. You already know what to assert. Experimentation, on the other hand, generates new knowledge. And so from a chaos engineering perspective, that looks something like this. You create a hypothesis that your system can tolerate some condition, and then you create a control group and experimental group, and you apply that condition or event to the experimental group, and you see if that changes the output of the system. If it doesn't, then you have more confidence in your hypothesis. If its output is different, then you've disproved your hypothesis and you go create a new hypothesis. In this specific case, if you disprove that hypothesis, maybe you sit down with the service owners for that microservice that was affected, and you go, hey, just so you know, when you lose a database, the whole system does something bad. So we have some advanced principles that we built up based on our own experience and our projections of where we'd like to see chaos engineering go. The first is that you build a hypothesis about steady state behavior. So you want to look for KPI or some metric at the boundary of the system. As engineers, we tend to have a penchant for trying to figure out how things work internally. And that's useful, but that's not the purpose of chaos engineering. Chaos engineering is trying to determine if something works, not how it works. We are not validating the model of how the software works. We're verifying its output. So it's good to mentally be able to navigate towards that star. Vary real-world events. So again, we're not making assertions about the correctness of a program or specific output of the program. We want to do things that experientially we've actually seen. So generally, these things look and sound, feel like failures, but there's a difference between chaos engineering and failure injection or failure testing. So this looks like servers disappearing, latency. It also looks like positive things like sudden increase in traffic, or just new interactions between different microservices that aren't really good or bad. Experiment in production. This is important because if you are capturing user traffic and replaying it in a test environment and running chaos experiments there, then you're building confidence in your test setup, not in your production setup. Customers, they do weird things. And the only way to truly capture that and build up confidence around the system in production is to test that actual system in production. Clones aren't quite as advanced. They don't give you the same level of confidence. And finally, automate your experiments to run continuously. So particularly at a place like Netflix, where you've got continuous delivery of hundreds of different microservices, things are changing too fast for somebody to manually be able to test things to give us the kind of confidence that we want. You have to work towards automating these and making these part of the continuous delivery system. Those are our posited advanced principles of chaos engineering. And we put those out there on Principles of Chaos, and we saw that there was some good energy in the community, so we started developing this community. We call it the Caste Community. And we have a Chaos Community Day. 2 years ago, we ran one in San Francisco with the usual suspects. Last year, we ran another one in Seattle. There might be people here who are interested in doing chaos engineering. If you are, I'd suggest you go there, and at the bottom you'll find a Google group for Caste Community. You can join there and see the announcements, the notices that we'll post for upcoming Caste Community Days. And now I want to touch on, again, how this looks in production at Netflix. So say we have an experiment where we want to test whether our API service is resilient to a failure of our personalization service. So personalization might be the service that recommends the movies that we specifically think you would be most interested in watching. Yesterday, Colton spoke about Fit, which is a tool that he originally wrote that allows us to do this. We can say at the gateway, randomly select about 10% of, or on a sliding scale, we'll say 10% of the requests to participate in this experiment. So on the left, you've got some blue dots representing requests coming into the gateway, and some of them, 10% of them, get tagged. So we're actually injecting into the request header some additional context. And between the client libraries for the different services, we have these injection points where Fit can test and see if the request header matches a certain clause, then it can fail it out. If it doesn't, then it just continues to propagate the request through the system. And of course, a real request would fan out, but we can view it linearly like this. It's a little bit easier. And so in this case, when the request in the experiment goes from API to personalization, the client library there can just cancel it. We can add a failure there, we can return an error, or we can just let it time out. So say we return an error. In this case, we're trying to see, for 10% of traffic, if we're failing out this personalization service, is there an effect on our stream starts per second? This is our KPI, our big business metric that's very predictable for us. At any given point in the day, we kind of know roughly how many times people are clicking play, because there's a lot of people, so the variance is kind of low. This is taken from a real experiment where we tried that, and the arrow's pointing to the time that we turned the chaos experiment on. Did it have an effect? Hard to say. There's something there, but a couple things can happen. One is a user's device might make the request. They get tagged. They're in an experimental group. Personalization doesn't work. It returns an error, and the device retries. And when it retries, it's not an experimental group, so then it succeeds. So we wouldn't see that. In the other case, maybe the personalization does have great fallbacks, and it is returning proper response. And again, so it succeeds. So we wouldn't see that either. So there's a couple problems with this particular approach. Another problem with Fit as a tool is that we're affecting 10% of traffic here with this experiment, which means we pretty much can't run any other experiments concurrently because we've got a population that's just too large. So really what we knew we had to do was figure out a way to make the tool more precise so that we could focus in on a better experimental setup. Which brings us to our latest entrant into the Chaos toolset called CHAP, Chaos Automation Platform. And what Chaos Automation Platform does is for the service that we're interested in looking at, it'll spin up two new clusters, a control cluster and experimental cluster, and it'll apply the experimental condition, the variable, to the experimental group, and then it'll compare the KPI of the results at the output. So using the same visualization for that diagram, it looks something more like this. Instead of all the requests going from gateway to API, we have an API control and an API experiment, and we can select 1% of the requests for the control or something smaller, and 1% of the requests for the experimental group, and we can make sure that those selections are based on particular users. So if a user is designated as being an experiment, they stay in the experimental group. So we're not worried about retries messing up our signal. And so those are tagged in the request context at the gateway. And then those requests propagate. Most of the traffic continues through the normal production path. Some will go to the control group, and some will go to the experimental group. And then, of course, the request that goes to personalization is errored out for the experimental group. And this gives us two very clean groups to look at, the control group and the experimental group, to compare. And the color of the lines doesn't really matter too much here, but the blue group is the control group, the red group is the experimental group. Here's the SPS for the requests that went through those two groups, and you can see that they're roughly the same. So this lends confidence to our hypothesis that this type of failure does not affect our stream starts per second. The fallbacks and personalization are adequate. They're pretty good. Here's another way of looking at that. We have our fallback metrics. On the left, you have the counts of successfully serving the request from personalization. For the control group, that's a number. For the experimental group, it's a flat line at the bottom. And on the right, you have the counts of fallback success. So for the control group, that's a flat line on bottom. It didn't call any of the fallbacks. And for the experimental group, that's a number that varies over time because it was using its fallback. And here's a comparison of CPU utilization. So you can see for the experimental group, CPU utilization was a lot higher. So apparently it was doing something, and it worked because the video continued to play. So as we thought about how to bring this to other organizations and to analyze our own place in chaos, internally at Netflix, our own sophistication, we chose to create what we call a chaos maturity model, because overloading acronyms is always fun. So this is our CMM. And we have two axes for this. One is sophistication, and the other is adoption. So under sophistication, we can look at things like how close is the practice for a company or a given tool using those advanced principles. Are we building our hypothesis about steady state? Are we varying real-world effects? Are we running things in production? How automated is it? And other things like, do the experiments self-reflect? Did they know to stop themselves if bad things are happening? That's important. Are they precise? Are they affecting a wide swath of traffic, like 10%? Or can they focus in on a small amount so that we can run many, many experiments in parallel? And we contrast that with adoption. How many users are internal customers are using this out of the potential base? That's an easy way to measure adoption. Another is What's the buy-in from leadership for doing this in the first place? Are there obstacles from leadership or peers to running chaos experiments continuously? And if you put these two together, we can come up with a nice, I won't say magic quadrant in the upper right, where we have at least our self-assessment for these two tools. These were both chaos pioneers. Internally at Netflix, we've got very high adoption for both tools. For the things that they're trying to solve, both of them are very sophisticated. And about half a year ago, when we started out with CHAP, it didn't have much of a chaos story, very little adoption, and it wasn't very sophisticated. So the first thing that we decided to do was make it more sophisticated. And generally today, we self-assess that it's somewhere up here where we do have feature requests, features implemented, such as the experiments will stop themselves if it's giving our subscribers, our customers, a bad experience. It's also integrated into our continuous deployment pipeline now, so that it's part of just naturally serving a service. But we don't have high adoption. So our next task as chaos engineers is to increase adoption, and we've taken our tier 1 services and had them play around with it and gotten some feedback, and now we're looking at expanding out for our tier 2 services and then more broadly at Netflix. So just to hammer this point home, I'll give you one more example of a hypothetical systemic effect. In a previous life, I lived in Philadelphia, and I worked in Washington, D.C. a lot, and I liked the show House of Cards. Has anybody here seen House of Cards? Right? This is the brilliance of Netflix. They took something boring like presidential politics, which has absolutely no drama, and they made you actually want to watch it, right? So on a train to D.C. at night is the best way to watch House of Cards. So I'm sitting there with my laptop propped up on my leg, and I'm drinking my coffee. And this is totally made up story, right? This didn't actually happen. And in the second season, something particularly surprising happens in a subway. And I was surprised. So I went like this with my hand, and coffee spill on my laptop. And I'm like, oh no, and I'm grabbing napkins, and I'm trying to, and it's not playing anymore. So I do what any user does. I start hitting refresh and trying to reload it in my web browser. And of course, I don't know what Amtrak does. They use the cell towers or satellite or something. So network partition. So I must have hit reload 1,000 times. And those requests all back up in, I don't know, Chrome or the cell tower behind the network partition, and then it finally goes through, and I get back this weird screen from Netflix that I haven't seen before. Again, I'm just making this up. So what happens on the Netflix side? Well, again, we have great engineers, so they've done great things. So there's a microservice for personalization and another one for users, and a smart thing to do for the user's microservice might be, containing just data about users, would be to use a consistent hash function to make sure that requests for any particular user goes to the same machine or same group of machines, so that every machine doesn't have to have the whole world of user data space. They can just have a smaller pseudo-random shard of that data. And they might have other useful things in there, if they can't get the latest data from the canonical source, the database, maybe they'll serve requests out of cache. And of course, each engineering team at Netflix is responsible for the operations of their microservice, so they're going to have things like scaling rules. So if, I don't know, the mean load on the machine goes, on the cluster goes up, the cluster will scale out, and if it goes down, the cluster will scale down. And on the personalization side, they'll have things like smart fallbacks. If it can't connect to the user service, then maybe it'll just give you a default experience. Instead of the shows that we think you would most like to watch, just the most popular shows. I don't know what that is today. Luke Cage or Orange is the New Black, whatever the most popular shows are. Zootopia. So all of a sudden, this user microservice gets 1,000 requests for the same user, all get directed to one particular node. That node goes, oh, well, okay, the connection to the database isn't returning this same request over and over fast enough, so I'll flip to serving things out of cache. Great, now responses start going back up. Of course, serving things from cache lightens the load on the server, so the mean load goes down, and the cluster does the responsible thing and shrinks. So it gets rid of maybe that node because that has less load, and distributes the work to another member on the cluster. And while it's moving responsibility for that data, maybe it times out and it's a response to personalization. So personalization returns a default experience. Again, hypothetical example. So what does that look like for me on the train? Well, now I see something that I haven't seen before, recommendations for shows that I would clearly never watch. So I do what any reasonable user does. I try turning things on and off again and hit reload 1,000 more times. And so all of those requests go back, and the same thing happens. They all go to the new node that has responsibility for that user now. It flips to serving things from cache, which means that the average load goes down, so the cluster shrinks, and while it's moving data, now for a few users, personalization has requests timing out, so it serves a default experience to more users. So now more users see this weird screen recommending movies that they would never watch. So they start hitting refresh because, what's a user going to think? But this is broken, so I should flip it off and flip it back on. So now we've got a user-induced retry storm. And more traffic comes to the user microservice, and the whole thing flips to serving things out of cache. So the average load goes way down, so the cluster shrinks until it's just one node, and then that falls over, and the whole service stops. Because I spilled my coffee. So again, that didn't actually happen. Totally made that up. But I think it's a good example of the kinds of things, the kinds of systemic effects that we're trying to protect from. Because in that case, none of those rules for resiliency or for responsible scaling, none of those rules were wrong. They were all good ideas. It's the combination of those rules that, and there's too many rules for any one human to hold all of them in their head, it's the combination that can lead to systemic effects that are undesirable. So I'm at least my clock is telling me that I have enough time to briefly delve into another topic near and dear to my heart called intuition engineering. The thing that the teams that I manage have in common, the traffic, chaos, and intuition teams, is that they all have a focus on availability. And rather than understanding any particular feature really, really well, all three of those teams have to understand a holistic understanding of the entire system, right? The traffic team has to understand how the global state of the system looks at any given time if they're going to move traffic from one region to another. Chaos team is looking for systemic effects. And so we came up with this concept of intuition engineering to allow the traffic team in particular to be able to understand the state of the entire system at a glance. We've got great metrics and analysis tools. And if we want to dig into charts and figure out how the entire system looks, we can have dozens of charts up that we'd have to read through and figure out whether the whole system is behaving as expected. But we wanted just one thing that we could look at and in a glance understand the state of the system. So as we were kicking this idea around, we came up with a metaphor for how we thought about this. And it's an absurd metaphor, but I think it's instructive. So we said, imagine that we made a suit. And this suit is covered with electrodes. And the placement of the electrodes correspond to different microservices. We affectionately call this the pain suit. And when you're on call, when you volunteer to be on call, you have the privilege of wearing the pain suit. And our hypothesis is that after not too long of wearing the pain suit, you'd kind of just intuitively know the state of the system. You wake up at 3 o'clock in the morning, your shoulder hurts, you're like, oh, the reverse proxy is down again. Like you would just kind of like feel it, and somebody could turn to you and ask at any given time, hey, how's the system doing? And you'd just be like, yeah, it's pretty good. Or, yeah, we got to look at something. Now, we haven't built the pain suit yet, but we did build a visual analog of it called Visceral. And you might have seen this at the booth out there, but in case you haven't, here's the main screen. And what you have here are a bunch of dots moving. The circle in the middle represents requests coming in from the internet, and the 3 points of the triangle are the 3 regions that our control plane is served out of. So we have US West, US East, and EU West. And in about as long as I've been talking now, your brain just sort of figures out what normal looks like in terms of volume, speed of the requests, color. Most of these are blue, but you might occasionally see red ones, which are failures, and yellow ones, which are fallbacks. And so when the traffic team needs to adjust traffic around the globe, we can just glance at this and just know, okay, yep, that looks right. Or in the case that something is wrong, we glance at it and we go, something looks wrong. And your brain just kind of knows what normal is. It becomes very intuitive. And that's my very high-level introduction to intuition engineering. And if you want to know more about that, again, there is a demo of this and the microservice view of this interface, open source project Visceral at the booth. And now I've reserved time for questions.
Hi. Peter Sahlstrom, MailChimp. What is your expected impact on customers when you're doing this? Like, are you aiming for no visible customer? The customer doesn't observe any kind of an outage or impact at all?
Yeah. If we think the customer is going to be impacted, then there's no need to run a chaos experiment. If we already have that suspicion, then we should go figure out why we suspect that and fix that thing. You should only be running chaos experiments if you already think that your hypothesis is true.
Okay, thanks.
Hi, thanks for the talk. Lucas Ewalt from LinkedIn. When you showed the magic quadrant of chaos culture, what things did Netflix do to build that culture and make it so it was well adopted and used by every team?
What did Netflix do to make sure?
To increase adoption of doing chaos engineering so all the teams are using it.
So when you create a new service at Netflix, it defaults to having Chaos Monkey on. So that helps. We did not go through and turn it on for other services, but we thought about it. But we don't have to, because it's at least at this point, it's so much a part of our lore and our culture that it's pretty well adopted, and the engineers are just welcome. They've seen the benefits essentially already.
Are the service owners for all the microservices, are they the ones typically setting up and defining experiments that would impact their service, or is it more there'd be a team of different folks that are investigating reliability stuff stack-wide?
Historically, the chaos team has functioned from a consulting point of view, setting up experiments and running them. That doesn't scale, which is why we built CHAP. And we expect when CHAP reaches wide adoption, it'll be because it's a self-service tool where the service owners are setting up and running their own experiments.
Cool, thanks.
Yeah. Chaos Monkey is self-service, by the way.
Hi, I'm Adrian from Google SRE. So you mentioned that Chaos Monkey is on by default for new services. What do you do with the services who turn Chaos Monkey off?
The first thing we do is we go talk to them and ask them why. And so that falls into two camps. One is we didn't really know what the benefit was. Maybe it's a new team or something like that. and we just correct that misunderstanding and run it. There used to be a group that had specific needs for Chaos Monkey, like running a Cassandra cluster, for example, where you need n equals 3 in certain regions, things like that. So we modified Chaos Monkey to conform better to their use case. And the third group are internal customers, people who essentially don't have a valid use case for it. They're not in the critical path. They're not part of streaming. Maybe they run batch jobs, things like that. And so running Chaos Monkey just doesn't provide any value for them.
Cool. Thanks.
Yep.
Hey, I'm Saru from Bloomberg. I have a question regarding the test subject selection for your in CHAP. You mentioned you selected 1% of the traffic to go to control and 1% to go to experiment. Are those 1% actually the requests, or is it a particular set of users, a particular set of sessions? Because if it was just requests, then if you retry, the same thing that you mentioned can happen as before, right?
It's 1% of sessions.
Sessions, okay.
Yeah. So that was one thing that we fixed going from just using Fit to CHAP, was making sure, we call it sticky users, right? Making sure that those users are continually routed to either the control or experimental group if they're assigned to one of those.
Mm-hmm. And when you mentioned you were testing the fallback for your personalization service, were you referring to another instance of the personalization service, or were you referring, what did you mean by the fallback?
So the personalization service itself could say, if I don't have enough data or if I can't communicate with my downstream dependencies, I'm just going to serve this to my upstream instead.
Got it. Thank you very much.
Yep. I think the last question.
Hi, Tyler Stewart from Home Depot. So the question that I have specifically kind of going to that, how you're picking a certain percentage of users or sessions, was there anything that the service owners had to do to ensure that logic was met, or is that all done within the automation tool or the chaos engineering team?
That's all done with the tool CHAP. Yeah. So we don't want to burden them with that kind of computation. Cool. All right. Thank you very much.